Welcome. Now let us look at some of the other variables which are somewhat easily measurable and more importantly for which data is available in terms of tables and figures in various sources, including the appendices of your textbook Smith, Van and Abbott. We are going to look at two things: expansivity and compressibility. Once we have some values associated with these, that gives us an easier way of relating things to unknown aspects. Expansivity is defined as 1 by V dou V dou T at constant P. That is the definition of alpha, the variation of volume with time or specific volume with time at constant pressure for which is normalized with respect to the volume itself, the specific volume itself. Let us call that equation 238, and compressibility, which is given the symbol kappa, is defined as dou V dou P at constant T, the variation of specific volume with pressure when the temperature is held constant, and that again normalized with respect to specific volume and the negative of it. Let us call this equation 239. So with these two definitions, it is much easier to get a feel of these of the use of these definitions, alpha and kappa, compressibility and expansivity and compressibility, if we work out an example or an exercise. That is exercise 2.4 here. For a closed system containing 1 mole of a pure substance, express the variation of entropy, enthalpy and internal energy. These three are somewhat more difficult to measure. The variation of these with pressure for an isothermal process in terms of more easily measurable properties such as pressure, volume, temperature, alpha, kappa, expansivity, compressibility, etc. Note that this is an isothermal process and therefore the temperature is held constant there. This will take some thinking, so take about 15 to 20 minutes or so to work out this problem, and probably after about 10 minutes I will give you a part of the solution to help you in further solution. Okay, let us look at the part of the solution now. We have already seen, if you go back and look at equation 236, that dou S dou P at constant T is minus dou V dou T at constant P, and using the definition of alpha which was given in equation 238, alpha 1 by V dou V dou T at constant P, we get dou S dou P at constant T, the left hand side is nothing but alpha times V. This is dou V dou T at constant P, and we saw what alpha was. So this, the right hand side becomes alpha times V with a minus sign from here. Also we have seen from that equation 237, dou H dou P at constant T equals minus T dou V dou T at constant P plus V. Let me call this equation 240. I have started you on this process, so take some more time to see whether you can build up on this, develop on this, and get the internal energy, enthalpy and entropy in terms of easily measurable or variables for which data is available, such as P, V, T, alpha and kappa. Go ahead. Okay. Let us look at the remainder of the solution. Using the definition of alpha again 1 by v dou t at constant p, we can write the dou h dou p at constant t in the previous equation as minus T alpha v plus v. You can see this here, minus T alpha v plus v. Okay. And if you factorize a v out, you can write this as 1 minus alpha t the whole into v. Let us call this equation 241. So, this takes care of the variation of enthalpy with respect to pressure in an isothermal process, the constant temperature process, in terms of alpha, T and V very nicely. Now, let us consider internal energy. We all know that definition of enthalpy, which is internal energy plus PV, you can write U internal energy equals H enthalpy minus PV. And now, if you differentiate this expression with respect to P at constant T, note that we are looking for dou U dou P at constant T, and that is what we get by doing this. Dou U dou P at constant T equals dou H dou P at constant T minus, this is by chain rule, P dou V dou P at constant T minus V dou P at constant T, first function into derivative of the second function plus the second function into derivative of the first function. Of course, there is a minus here. Okay, all this done at constant T. Now, if we use the definitions of alpha and kappa, we can write dou U dou P at constant T, and we have already seen what the first one was, 1 minus alpha T into V. This dou H dou P at constant T is 1 minus alpha T into V, and this P dou V dou P at constant T is nothing but related to the definition of kappa, and this of course is 1. So, we do not have to worry too much about that. Therefore, you get dou U dou P at constant T is 1 minus alpha T into V plus P kappa V minus V, and V common out, you get kappa P minus alpha T into V. So, all this is in terms of kappa P, alpha T and the specific volume, all of which are measurable. Let us call this equation 242. So, that completes the relationships that we had needed in the previous problem, and what we are going to see next is some more useful mathematical manipulations from the point of view of classical thermodynamics applied to biological systems. There are of course many. I have chosen probably the most used ones to give you a flavor, so that you will feel comfortable whenever there is a need to apply these mathematical relationships. We will continue in the next class.